Today we are going to calculate Prim's algo time complexity via min heap. So suppose this is a graph and these are the weights over there, and initially what we are supposing that these are the nodes, or we can say edges A, B, C, D, E, F, as we are able to see in the graph. Initially we are supposing all parents are nil, and initially we are supposing its value as infinity. So in the similar way we have written over here like d parent is nil and d minimum value is infinity. Like that we have written on each and every node. So now we start. Suppose we are starting from A, because in min heap first one we need to delete, then only we can start that where we should go and like adjacent node. So first suppose we are deleting A. So we are writing here we are deleting A. So once we are deleting A, so its parent will be nil always, right? And so this will be the parent node for others, because first we are deleting A and its value will become 0 initially instead of infinity. So here in the similar way we are making changes here and we are writing we are deleting A. We are deleting A. So now we have to see all the adjacent node which are adjacent to A. So what are adjacent node? B. And what is the weight? 7. So A will be the parent of B. So we are writing here A, and the weight we are writing here 7. And C is also adjacent to A. So the parent of C will be A, and the weight which belongs to C is 3. And what about D? D is also adjacent to A. So the parent of D will be A, and the weight which belongs to this is 6. So we will write here 6. But the thing is that E and F are not adjacent to A. So that will remain same, that its parent will remain nil and the value will remain infinity. In the case of F also, parent will remain nil and value will remain infinity. So we can see here, because how many vertices are there, that much time it will take. How many vertices are there, that much time it will take to which one we need to delete, because this is the first one we suppose that we are deleting A, but next we have to find out that with minimum weight and we have to delete it. So we can say that if suppose n vertices are there, so like v vertices we are supposing, so log v time it will take. We can see from here, like now we can see that we need to find out which is the minimum. So minimum is 3 here, so we need to search it. We need to go through with all the vertices. So that's why we are saying that log v time it will take, because next we can delete which is the minimum one. First we can take anything, after that we need to find out the adjacent with the minimum weight. So log v time it will take in every time. So now we are deleting this one. This is what? C. We are deleting C. So again, how much time it will take? It will take log v time. Here also log v time, here also log v time. So now again, and here we can see we have to find out the weight of every adjacent node. So we have to go through each and every vertex. And we have to find out which is the minimum one. Here we can see, suppose that A is connected to, suppose as here 3. So we need to go to 3 only. But if A is connected to all, like this, if 2 edges are here also, so how much time it will take? It will take v log v time, because we have to go through each and every vertex and we have to find out what weight is minimum, and accordingly we have to change the weight. That we will see later here. So we can see here, once we are found out adjacent node to that node, so how much time it will take? It will take order of v log v time, order of v log t v time. Log v time because how many edges, or we can say vertex, are there, and but we have to go each and every vertex to find out that which is the minimum node, minimum weight, and what are the adjacent to that particular node. As from A, B, C, D only adjacent, but E and F are not adjacent. But if A and F also adjacent, then we have to go through all. So it depends upon that. So now we have deleted C because this is minimum. So for minimum finding out also log v time is required, because we have to find out, we have to search for individual each node so that we can compare and we can say that which is minimum. So this is deleted. Now because C is deleted, we have to change here also, that as we have done here. So the B parent is A now, and its value is 7, and C parent is also A, and its value is 3, as we have done here, and D parents is also A now, and its value is 6 here. E and F is not changed yet. Now when we are deleting C, so E and F are adjacent to C. So now its parent getting changed. So parent of E is not nil now, is C now, and the value of is 7. In the similar way, parent of F now, when we are deleting C now here, because this is the minimum weight, so we are deleting C. So after that the changes are here. So parent of F will become C, and the value of minimum is 5. So now we are going to write here in the similar way. So what we will do here now, and the, yeah, correct. So here also it will get changed. The C. Initially B parent was A, but now A get deleted, and now we are here C, we are deleting C. So the parent of B will become C. So here what we will write? Here we will write C, and the weight was 7. Now weight will be 6. So instead of 7, what we are writing? We are writing 6. So same thing we are going to write here. So instead of B here, the parent of B will be C now, and the value of, instead of 7, it will be 6, as we have done here. Now this is we are deleting, so no need to change. D parent is same. Why it is same? Why we are not changing? Because the value is same. Here. This is 6, so we are not changing it. So we are not changing it. It will remain same. So we are writing here A and 6, and here E, C and 7, F, C and 5. So now adjacent node are A and C. Adjacent node now we need to find out which one is minimum. Right? So which one is minimum here? This C, this one, this value. So what we are going to delete? This is F node. What we are going to delete? F node. So we need to cross check the adjacent node of this. So because adjacent node of this D, C is deleted, so no need to worry, and E. So only these two value we need to see, right? And A is also deleted, C is also deleted, so do not worry, and B is not adjacent to that, so we can't change anything. So B will remain same, C 6, and we are deleting F. So we need to cross check here. So the parent of D will become F now. F now, and the value is, because it is less than this, so value is 3. Instead of 6, what will come? 3 will come here. So in the similar way, we are going to write here the D value will be F, parent will be F, and the value will be 3. And what about E? E, we can see here, if we change E, so value will become more. Value will become more. So we are not going to change it. This is the, we are going to change value on parent when the value is less. But if here we are going to change, so instead of 7 it will be 8. So we are not shifting it, we are not changing it, it will remain same. So we are writing same thing here, C and 7. So now we are deleting F. We are deleting F. So now we are going ahead. Now what is minimum? Minimum is D here. Minimum is D here with minimum value. So we are going to delete this. We are going to delete D now. We have deleted A, C, F. Now we are going to delete D. So who is adjacent to this? No one. Because this all are deleted, so nothing will get changed. Nothing will get changed. We are going to delete D. So how much time it will take? Log V time. Whenever we are deleting something, how much time it is taking? Log V. Log V. Because we have to search which one is minimum. So how many number of nodes, or we can say edges are there, vertex are there, we have to search like this. That's why log V time. And how many adjacent are there, it depends upon that. So that's why it is order of V log V. If it are more in numbers, as I have said earlier, if A is connected to all, so we have to change all. If it is not, so change is less. So now what is left here? We will write here C6, C7, because nothing has changed, because once we delete D and all adjacent node are already deleted, so we can't change anything. So now these two, so which is minimum? This one is minimum, so we are going to delete this one. Delete B. What we are going to delete? B. So how much time it will take? Log V. Now we have to see what we can change here. If we delete B, so adjacent node is E, because rest all are deleted, only one is left, that is E. And we can see here, so now this value is 7, but if we change it with B, so value will become 4. So we can change it. So now E parent will be B. E parent will be B, and the value of 7 will be 4. Value will be 4. So we can write here in E. So here what we will write? We will write parent will be B and the value will be 4. Parent will be B, value will be 4. So only one is left. So we are going to delete this. Delete. This is B deleted, this is E. How much time it will take? Log V. Log V. So we can see here, and we can make first what we have delete A. So we are writing A, and the weight on A was what? 3. So we are writing here 3. After that, what we have delete? We have delete C. So where is C? C is here. So we are writing C and making graph. After that, what we have delete? We have deleted F. What we have deleted? F. F is here. C like this. So we are making F here. Right? What was the weight? 5, as we can see from here. So we are writing 5. After that, what we have deleted? We have deleted F, D. Deleted D. So D is here. F to D. F to D. And what was the weight? Weight was 3. So we are writing here 3. Next, what we have deleted? We have deleted B with 6 weight. So we can make like this because B is here from C. 6 weight. After that, what we have deleted? We have deleted E with 4 weight. So from B to E. So we are writing like this. So this is the final graph via Prim's algo using via min heap. But the thing is that we are calculating time complexity here. So as we are seeing, every time we are searching minimum weight, so log v time it is taking, because how many vertex are there, accordingly we have to search. And the thing is that how many adjacent weights adjacent edges are there regarding each and every vertex, that much time we have to change the adjacent if value is less than or not, but we have to go through with each and every vertex. So we can say simply v vertex, and how many time we have to go, v log v. So we can say best case is equal to v square log v, or we can say e log v, because it depends upon how many edges are connected to that. Like as I'm saying again and again, initially A is adjacent with 3 vertex, so we go through with 3 vertex. But if it is suppose connected to all vertex, so we have to go through all vertex and we have to change the weight and parent of each and every vertex. In the similar way, if B is connected to all vertex and after that we are deleting B, so we have to go through with all the vertex and we have to change, and we have to compare and see if it is minimum, then we have to change the weight and parent. So accordingly we have to go through. So that's why we are writing, instead of v square of vertex, we are writing h. It depends upon the edges. So we can say in worst case E is equal to v square. E is equal to v square. But in best case we can say E log v, and in worst case we can say v square log v. So the time complexity in best case we can say order of E log v, and in worst case we can say order of v square log v. Sorry, I need to supposed to write like this, E log v. So in best case E log v, or in worst case v square log v. So this is the time complexity of Prim's algo using min heap tree.